Welcome to the Technology Geek. Today, we're diving deep into the world of kernels, the vital component of our operating systems. Join us as we explore their history, mechanics, and benefits. Let's get started. The Genesis of Kernels. The first kernel in the world was called the monolithic kernel. It was introduced by a team of computer scientists led by Dr. Kenneth Lane Thompson and Dr. Dennis McAllister Ritchie at Bell Labs in the early 1970s. Their work revolutionized the field of operating systems and laid the foundation for modern kernels. Dr. Kenneth Lane Thompson and Dennis McAllister Ritchie, known for their contributions to the development of the Unix operating system, played a vital role in creating the first kernel. Their innovative approach and expertise in computer science paved the way for the birth of this fundamental component of an operating system. The precise date of the introduction of the first kernel is commonly associated with the release of the first Unix operating system, which occurred in 1971. Understanding the kernel. The kernel serves as the bridge between software and hardware, enabling smooth communication and coordination. It acts as the core of the operating system, managing resources, handling system calls, and ensuring security. Exploring the core of the kernel. In this segment, we'll delve deeper into the development and functioning of the kernel at its core. The kernel plays a critical role in the overall operation of an operating system, and understanding its development process is essential to grasp its significance. Kernel development. Kernel development is a complex and meticulous process that requires deep knowledge of computer architecture, hardware, and system-level programming. Developers use low-level programming languages such as C and assembly language to build the kernel. These languages provide direct access to hardware resources and allow for efficient and optimized code implementation. Designing the kernel. Developers consider factors such as process management, memory allocation, device communication, file system management, and security protocols. The design phase involves determining the appropriate data structures, algorithms, and interfaces that will enable the kernel to perform its tasks effectively. Implementing the kernel. Once the design is finalized, developers begin implementing the kernel by writing code in the selected programming languages. They create modules or components that handle specific tasks, such as process scheduling, memory management, and device drivers. Implementing the kernel requires in-depth knowledge of operating system internals, hardware architecture, and system-level programming concepts. Testing and refinement. Testing involves simulating various scenarios, stress testing, and debugging to identify and fix any issues or vulnerabilities. The development team iteratively refines the kernel based on the results of testing and feedback from the community or early adopters. By following this meticulous development process, the kernel gradually takes shape, encompassing the core functionalities that drive the operating system's performance and reliability. Exploring different types of kernels. Kernels come in various types, each with its own unique characteristics and functionalities. In this segment, we will explore the different types of kernels commonly used in operating systems. Monolithic kernels. Monolithic kernels are known for their comprehensive and all-encompassing design. They consist of a single, large kernel that handles all system functionalities, including process management, device drivers, and memory management. Examples of operating systems that use monolithic kernels include Linux and Unix. Microkernels. Microkernels take a minimalist approach by keeping the kernel as small as possible. They only provide essential functionalities such as process scheduling, inter-process communication, and memory management. Other services, such as file systems and device drivers, are implemented as separate user-level processes. This design improves system stability and allows for easier extensibility. Examples of operating systems that use microkernels include QNX and Minix. Hybrid kernels. As the name suggests, hybrid kernels combine features of both monolithic and microkernels. They aim to strike a balance between performance and modularity. Hybrid kernels provide a core set of essential services within the kernel, while other functionalities are implemented as separate modules. This approach allows for better performance optimization and flexibility. Windows NT is an example of an operating system that uses a hybrid kernel. Exokernels. Exokernels take a different approach by providing minimal abstractions and leaving most hardware resources directly accessible to applications. They prioritize flexibility and customization, allowing applications to have fine-grained control over resources. Exokernels are still an area of active research and have limited practical implementations. Each type of kernel has its advantages and trade-offs, and the choice of kernel depends on the specific requirements and goals of the operating system. Exploring popular operating systems and their kernels. Let's explore some of the popular operating systems today and the kernels they rely on. Each operating system has its own unique kernel, shaping its functionality and user experience. Linux-based operating systems. Linux kernel. The Linux kernel powers a wide range of operating systems like Ubuntu, Fedora, and Debian. It is known for its stability, security, and open-source nature, allowing customization and community collaboration. Windows operating system. Windows NT kernel. Windows operating systems, such as Windows 10 and Windows Server, are built on the Windows NT kernel. This kernel emphasizes compatibility with a vast range of software and hardware, making it a popular choice for personal computers and enterprise environments. macOS. XNU kernel. macOS, the operating system powering Apple's Mac computers, utilizes the XNU kernel. This hybrid kernel incorporates elements of the Mach microkernel and the FreeBSD kernel, providing a stable and efficient foundation for Apple's ecosystem. Android. Linux kernel. Android, the widely used mobile operating system, relies on the Linux kernel as its core. This kernel provides the foundation for device drivers, memory management, and process scheduling, enabling the Android ecosystem to flourish. iOS. XNU kernel. Similar to macOS, iOS, the operating system powering iPhones and iPads, also employs the XNU kernel. This kernel ensures optimized performance, security, and seamless integration with Apple's hardware and software ecosystem. The first company to embrace kernels. Microsoft was one of the pioneering companies to embrace kernels. They integrated the Windows NT kernel into their operating systems, which played a huge role in making kernels popular and changing the way we use computers. That concludes our exploration of kernels, the core of operating systems. We've covered their history, inner workings, and benefits. Understanding kernels helps us grasp how our computers function. I hope you enjoyed this journey. If you found it helpful, remember to like, share, and subscribe to the Technology Geek for more exciting tech content. Thank you for joining us, and keep exploring the ever-evolving world of technology.